So let's talk about real stuff, like implementing a processor stack. So I think that's going to be the most interesting thing out of the rest of this. Because we have, let's see where we're at. So we got program. So they have a thing in here, load and store with offsets. That's effectively what we've already done. That would allow us, I guess, technically to implement like arrays type things, where you can load something into a base address at bucket 4, something like that. Oh, just before I forget here, let me, yeah, it's recording. Let me show you a example of how we can tell, and we'll just do this in C because that'll be fun. Huh?
That's my favorite.
Is it?
PTSD from C.
I do too. That was a bad class.
Ani was the only good thing in that class.
Which class was it?
Yes. I don't even remember. 450. Yeah, it was 450.
It was 4 something.
450 because 470 was this class.
No, whatever. Standard IO.h.
I don't remember what it was called.
So what we've been spending most of the day doing is this idea of interrupting the CPU to do input. Then we ultimately come back to the CPU. And we want to see that that's expensive to do. So for instance, if I, we'll just say int main, int argc, char pointer, argv, something like that. And so let's say I have like a, a loop that goes through 100,000 times. And I'm going to just say int count and start that off at 0. And I'll say count plus plus in here. And then at the end, I'll do a printf. The count is something like that. All right, so that program ran really quickly, didn't it? I mean, felt instantaneous. All right, so now we'll come back in here, and I'm going to take this line. Oh, what is it?
Oh, you put the display inside the loop.
Yeah.
That's expensive.
So I'll do the count plus plus in there. So same code as I had before, except I'm printing each time through the loop. I'm interrupting my CPU. I'm signaling my CPU through 8192 that I want to do input. I'm reading the input into, well, actually this is output. So I'm signaling my CPU that I'm going to do output, and it ultimately is outputting to the screen. So it's going the other direction. We're doing the same thing. We're giving control away from the CPU to the operating system. Took longer to run?
Yeah, that's
And if we really want to see it happen, let me just steal this line. Let's have this go through a couple extra times.
That will not stop.
All right, so definitely taking some time.
That's kind of fun.
And if I stop that, I go in here and I edit this. I just comment out the line inside.
It'll be instant.
Significant time difference, right? right? That's what's happening to our CPU under the hood. Every single time we go to do output, it's setting a register, it's turning it over to the OS is displaying it. Back to the CPU. Set the register, turning it over to the OS to deal with it. Back to the CPU. That's why it takes so much longer to do it as opposed to just doing math in there instead of output. So I/O is expensive, something to kind of keep in mind in general about architecture. So if you're writing any sort of code for anything, you know, when you're testing, it's handy sometimes to just do some outputs here and there. But if you've ever been working in a language that has an option between a log, where you can print something to a log, or you can actually do like a println. So like in Java, we could do system.out.println, but there's also a log output in Java. And what you can do is when you, and actually Java is not the best example. A better example would be, well, we could just use the example with Java, it's fine. We can compile with debugging on or with debugging off. And what that allows you to do is if you always do logs instead of system.out, system.outs are just standard output. But if you always do a log, like you're doing a debug, so like a debug.log, then you can compile your program normally and those things will show up to the screen for you, the user, seeing that, oh, I'm getting my output, that's what I wanted to see there, everything's working. Then after you've tested your program, everything's good, when you do a final compile, you can compile for production or with debugging disabled. And what it'll do is it'll ignore all the log files at the assembly level. So it'll recompile your code. You won't have to go through and comment out all your debug code. You can leave that stuff in there, but you're compiling it to ignore the debug so that what's actually in your final assembly instructions will be fast code without outputs. If you always choose to use the debugging system for the language you are working with, as opposed to using the standard I/O stuff, which it's not going to know between what's debugging and what's supposed to be output for that language. All right. So let's do this program stack thing real quick, and then I think outside of stores with offsets, well, let's look at the stores with offsets real quick. Maybe it only takes a second. Actually, why don't we just talk about both of those things? That might make more sense to finish this off, because one weakness we have right now with our code, and it's actually not a problem, we can fix it pretty easily, it'll just be a little bit tedious, is if we go up top here, you know, we have a pretty kind of hacked together data memory. You know, we gave it some addresses here, and then we just gave it some special addresses here at the end, you know, to make it work. Realistically, we would probably want to fill this guy up with a whole bunch of memory, right? If we think about our memory inside of our computer, it's like one gigantic long street with 4 zillion things on it. So you would have memory address 5,000, 504, 508, 12, 16, 20, 24, 28, on and on and on and on and on until you have a gigabyte of memory, 4 gigabytes of memory, whatever, something like that. At that point, it might make sense for you to say, oh, I want to go to base address 5016 and put at bucket 2, which might be here, the number 7. So that's a store with offset. Make sense? So if we go back in here, it's saying, so if we load into, so the starting point up here. So we're going to load into some register 0 and then the memory address. So this says load in there whatever's at that memory address, this register. So that gives us that base address. But if I say load word into a register and offset from a base address, that allows me to say things like base address T6, whatever's in T6, take 4 steps from that. So T6 holds 5032. 5032 plus 4 is 5036. That makes sense? So I'm going to load into T0 whatever's at 5036, which is the 70. That's what this line says. Store inside of register T0 an offset of 4 when starting at this memory address. So start at T6, which is memory address 5032. Add 4 to that, 5036. That's the value. Store that in T0. That make sense? Load word into T1. Go to base address T6, 5032. Add 8 to it. So it's going to be 5040. That's a 55. We should find in T1 a 55. T2. Go to base address T6, 5032. Walk 12, 5044. 23. That's what we find in T2. See how that, so this is kind of like a, if we wanted to do an array with this, and we would call this, let's call this a array of ints, 4 bytes. Let's call, when we add 4, we're going to call that 4 bytes. So this would be bucket 0, bucket 1, bucket 2, bucket 3, bucket 4. So if we stored our base address, so 5032, this is actually our base address. So this is bucket 0. Bucket 1, bucket 2, bucket 3 in this little example of, so for, it wouldn't be very hard to write this. LW and SW, the tedious part would be giving ourselves a bigger memory space. To write something instead of here's our 8 buckets of memory for us to just mess with. We would probably just write a function that just changed memory to be this giant thing and move on with life. But, all we're adding to this is saying, find this place and then add to it this number, and that's actually the place in direct memory or in data memory that you want to work with, is this address plus this number. Not too bad, pretty straightforward. All right, so just for the sake of time, we won't implement that because we'll spend half that time implementing our bigger memory space. Okay, so that's our offset stuff. Then our stack stuff. Remind me, what's a stack data structure? First in, first out? No, that's a queue. Yeah, so last in, first out, LIFO. It's up. Oh, you said the other thing? It's so early though. What's up?
This is not early. I'm usually asleep by now.
I got a 4 a.m. Zumba class I'm teaching.
I know.
Serious?
Yeah. You've never gotten to a Zumba class?
No.
It's so
I
fun.
do a 4 a.m. Zumba class on the Bluff.
No way. And I want to live stream this. I'll get up at 4.
You gonna come to my Zumba class? So you wouldn't actually wake up to see if your fat professor's running a 4 a.m. Zumba class on the Bluff. Or you wouldn't actually get up at 3 a.m. to come and see if your fat professor is running a Zumba class on the Bluff. He's like thinking about it. He's like, no, but maybe.
Okay, so you had to be up even earlier.
What, for the Zumba?
We need to leave. We need to wrap this up. Yeah.
Chop, chop.
No, we're done at 10, regardless of whether I'm babbling or... All right. Chop, chop.
Long story short, that's what I was thinking of. I just said it the wrong way.
Oh, okay, well, it's wrong.
You're right.
You. Okay, so subroutines with program stacks. So a stack is a last in, first out queue. So we do pushes to push things onto the top of the stack. We do pops to remove things off the stack. So this is kind of a special implementation of this offset type thing. All right, so we, these aren't the actual instructions here. They're just telling us if we push T0 onto the stack. So in their example here, I think they're treating the stack as 8188. Is that it? I don't even want to use that. Let's just go down here. Yeah. So there's this new pointer now called the SP stack pointer. And the stack pointer is holding value 8188. Why? Because that's this architecture in conjunction with, let's say, the OS has decided that is the memory address word that has been reserved for the stack. And it's actually an important thing to wrap your mind around this, because that's not infinite, that stack. You know, if you've ever written a recursive function that was infinite recursion, you never broke out of it, then what ended up happening is you typically, like in Java, it'll say out of stack space. All right, because it'll say, look, because every single time it calls a function recursively, what it did is it put that current function on hold at the top of the stack. Then the next version at the top of the stack, next version at the top of the stack, until, yeah, if you're not ever going to end your recursion and start popping stuff off that stack, you're going to run out of stack space. So your operating system or whatever architecture you're working with, it will kind of depend on who's going to drive that decision about the stack space, but system memory is managed by your operating system. So this would be Windows or Linux or whatever that's going to say, for our operating system, the way we deal with things is we have this chunk set up for stack space. And it might be configurable. You might be able to go into one of your configure files or something like that and change the default stack space to be bigger or smaller or something like that. But remember, we talked first week of class, I think, about kind of the job of a compiler is to take a architecture and to take a operating system and give you assembly code that works in terms of those two things, right? Remember that? All right, so when we have our code here, our assembly code, it's written in terms of what we're looking at here is the fictitious operating system that happens to say it has a stack that begins at address 8188. That's what it says, for whatever reason. And by our example here, that 8188 is right here, and it looks like it goes to 8172 if we just pretend like this is the biggest stack they give us. All right, so when this pushes T0 to the stack, so we're going to add to our current stack pointer a -4, so that's going to change the top of the stack. So it was an 88. Now we're adding a -4, which is how we implement subtraction. We do subtraction through addition. So we are going from an 88 plus a -4 to an 8154. So that's the new top of the stack. Or that's the new next place we're going to put things onto the stack. All right. So then we're storing into T0 whatever the current value at stack pointer is. All right, so that stores a word. Oh, actually, I'm sorry. It stores a word from T0 to the current stack pointer, which would be, I guess, did they already put a value into that? Or are they moving it to 5? Oh, T0. They just gave us a starting point for it. Here's T0. T0 is a 5. So they added to it. Here's the 5. So when we push that onto the stack, we're putting a 5 now at the top of the stack. Then we're going to put whatever's in T2, which is, well, it's just a horrible example. Use the same number twice. All right, we're just scrolling down. That's a terrible example. All right, but in any case, you have your stack, starts at 8188 memory address. So this pointer, just like our RA pointer, which remembers where's the place you need to return to in your code, the stack pointer says this is where your stack starts. And anything off that is going to be an offset from your base stack pointer. All right, but stacks work as a last in, first out. So when we push something onto the stack, we're piling it on top of the previous thing. Okay. Okay. So, and we kind of saw this a little bit before, and let me actually just connect this back to what we saw, because we looked at an Intel architecture Hello World program in Java, right? So Linux Hello World assembly. Okay, now this guy does not use a stack. So effectively, we're trying to accomplish something. What does he do? Now, I'm not making a direct comparison here because we're actually preparing some things for a subroutine that's actually owned by the operating system. That's our syswrite subroutine thing here. So instead of using a stack, what did we do? We just stored some values in some very specific places. That's kind of like what we implemented today with the I/O.
Yeah.
You know, where we had to put something, if we wanted to write it out, we put it in a very special spot.
Right.
If we wanted to read something in, we kind of had to trigger a special spot, and then that fired the read-in thing, and then that stored the whatever you input into a very special place. Okay, so this idea of moving values into a register, moving a value into a register, we call our registers T0, T1, T2. They call their registers EDX, ECX. That's the Intel architecture as opposed to the MIPS architecture. All right. But this would be an example of kind of loading parameters into registers rather than what the book's about to talk about, and that is storing the parameters for a subroutine, inputs that you want to give to a subroutine, onto the stack rather than having to burn through your registers, especially in our example architecture here where we don't have a zillion registers. You know, by this example here, we have a 0 through 4 register and a stack pointer. And I think we could probably assume we still have an RA from the last subchapter, but whatever. But this supports my example here enough where we don't have a zillion registers. And the registers you have, they're expensive and they're very fast. You probably don't want to waste those registers if you don't have to. And you might already have stuff stored in them that you need. So kind of the idea is what if I have a subroutine that's going to need to operate on 3 or 4 inputs, 3 or 4 values. When we write a function in Java or function in C or C++, whatever it is, we usually pass it 2 or 3 or 4, whatever it is, inputs for it to do its job. So what are our options? We need to get data into a subroutine. Well, one option is, well, we could just load the data into 2, 3, 4 registers and then write our subroutine in terms of those 4 registers. If he's going to add the sum of those registers, he'll go in and add T0 to T1, storing the result in T0, then add T0 to T2, storing the result in T0, and things like that. He could choose to do that. Or he can choose to look for maybe he expects 4 parameters. The 4 parameters could be prior to calling the subroutine, prior to doing a JAL, they could be pushed onto the stack. Push 4 inputs, your 4 inputs onto the stack, and then the first thing you do inside of the subroutine, or when you need the values, you start popping them off the stack to get your 4 values. Now you didn't really burn registers on your way in, but you might use them, right?
Yeah.
But if you keep using the stack, you could bring it off the stack and maybe you just have 1 register. You do some math and you push it back onto the stack. Pull it off the stack, use 1 register, do some math, put it back onto the stack. So you can use that stack as kind of extra storage that maybe doesn't have to be the absolute fastest. That makes sense? All right, so a stack can help us leverage more memory than we have registers, something along those lines. Similarly, we can store our return address. So instead of having an RA register, we can store that kind of value to the stack and do a push and pop off of that. But the stack is stored in data memory, which means it is slower performance than the registers.
Mm-hmm.
So we are trading that off. But by having that stack, which kind of acts like unnamed registers, right? We have to kind of use the push and pops to manage the current stuff stored in the stack. we get a whole lot. I mean, if you think about a processor, even the real full implementation of the MIPS processor has probably, I don't know, 16 or 32 registers. I don't remember what the actual architecture dictates, but it's not a ton, right? Where, hey, if we have 4 gigs of RAM, let's give ourselves 300 megabytes of stack space.
Yeah.
That's a lot of registers when each register is 4 bytes or something like that, right? Okay, so you can expand your storage capabilities of your architecture substantially by deciding that some things are okay to be on the stack at a slower performance when you just go and retrieve those parameters or something like that. Okay, so does that make some sense? All right, anything else I want to talk about from here?
I just have a small question about
Mhm.
CPU. So does that mean actually multi-core CPUs, each core has its own register?
Yes, because each core would be its own implementation of that architecture.
Okay.
Therefore, they would each have a T0, they'd each have a T1. That's where, and I don't even remember if this book talks about it or not. Does it talk about the caches, L1, L2, L3 cache?
I haven't seen it
Okay.
yet.
And maybe there's a section on memory maybe that it gets into it.
But yeah, that's CPU cache.
Oh yeah, here's a memory here. Yeah, so just kind of the foreshadowing is if you in a CPU, you have registers which are unique to a core, as he's calling it. So if you have like a dual core or a quad core i7, there's going to be 4 unique cores, and each one of those will have its own set of registers, super fast memory.
Yep.
Each of those cores will also have their own version of L1 and L2 cache. Faster than system memory, faster than data memory, but slower than registers. Okay, so L1 is pretty close to the CPU, so it's a little bit faster than L2, but also usually smaller, but bigger than a register. So it's kind of typically memory, the closer you get to the CPU, the faster the memory and the smaller the memory.
There's another question. Does actually the like L1, L2 also the relation between the physical memory is actually kind of similar to register to memory?
In terms of speed?
No, I say when, for instance, when you saying saving the data from register to memory, does that actually the saving to the cache first?
Oh, I see what you're saying. Yeah, there are some optimizations depending on the architecture. MIPS is probably older than that.
But it doesn't have that.
I guess I'm not necessarily positive, but certainly in newer architectures, they would have some optimizations where when you say, hey, I want to put something in system memory, and even though from a human's perspective, system memory is very fast, there might be some tricks where they immediately throw it onto cache, effectively get it off the CPU as quickly as possible, then turn it over to especially when you have multi-core processors where your CPU might be sitting there and have 3 of its 4 cores idle. Have the operating system do the final moves of getting something from cache over to real memory. Now, but with great power comes great responsibility, because now all of a sudden you could have a situation where you think you just stored something to data memory. You go on to the next line and maybe you're going to immediately use what you just stored, but it's still actually an L2 cache. It hasn't actually hit memory yet. So sometimes what you have to do is there has to be in the architecture kind of a fake requester who keeps track of where the current data you're looking for actually currently is. He might be earmarked to get back to real memory, but he might be currently stuck in L2, something like that. And then he'd be retrieved more quickly, which could be a benefit, but then you start asking the question, well, why did you store it if you needed it right away again? Probably a poorly written program or something like that if you were writing something to memory and then actually needed to access it the very next line. But then we have L3 cache, which is actually shared among cores.
Yeah.
So if you have a quad core processor, that processor would have a single chunk of L3 cache. So the operating system would use that L3 cache for managing things that needed to be shared among the different cores when you're trying to dual process stuff or quad process stuff or whatever. Okay, so that's that. Let me look at this machine instruction thing. So we always talk about computers speaking machine language. They actually hold collections of zeros and ones, right? And when we first night of class, I talked about CPUs as being kind of collections of magic tricks. Now, the reality here is, I'll blow this up a little bit. The reality here is that, for instance, load word here, what do we have? Well, they didn't give us multiples, but the actual instruction. So notice here that we have a 6-bit instruction for our machine code. All right, so a processor processes instructions in the form of zeros and ones, known as a machine instruction. Each machine instruction is 32 bits total. So your bit space for a MIPS instruction is 32 bits. Now, those 32 bits are going to come in the form of a couple of different things. The instruction itself, the things it's operating on, and then some values. So for instance, load word here has a 6-bit instruction code. So this is magic trick number. So this can hold up to 2 to the 6th power. 0 to the 2 to the 6 minus 1. So 2 to the 6 is 64 unique. So MIPS supports 64 unique instructions. Okay, that's how many magic tricks are on the MIPS processor. How do we know? Because the instruction space is 64. To have more magic tricks, we need a bigger, the instruction space is 6 bits.
Yeah.
So we can only uniquely map 64 things. If we needed more, we need another bit. Okay? So this is magic trick whatever. Our T0 is represented by this guy, and sometimes they have them in reverse order. So his T0 is 1000. So yeah, they do have them in reverse order here. So here's actually the T0.
5 bits.
Yep. And then your T6 is 1110. So this is your T6. So registers are stored as 5 bits, but notice that this register here is actually the second one. This register here is actually the first one here. And then this last place is our offset. We're only seeing a base value here, but we talked about offsets. So if it was an offset of 4, we would have a 1 here followed by 0, 0. Okay, so we get 16 bits of wiggle room down there for whatever the instruction has. Yeah, so store word, same thing. Add I. Notice that for all of these, the instruction size is always 6 bits. The register size is always 5 bits. And then we have this 16-bit chunk for, let's say, other. But this architecture does drive how many inputs our magic tricks can take, right? These magic tricks in MIPS have an opcode and really 2 parameters and then what it's operating on. Add I, destination, one of its registers, that's this guy right here. 100. Actually, it does it even completely backwards. So this would be T. So 1001 is T1. So this is this register. This is this register. And then the 15 is the immediate value stored here. This is the 1s, 2s, 4s, 8s. Add them together, you get a 15. So this is the binary version of the number 15. Make sense?
Yep.
For this guy, now look how they separated this out. They still had the total number of bits is the same. Okay, but they're calling the add instruction, which is this memory address. And then they have 3 different registers here. They're using this guy as kind of a nothingness, and I don't even know what they're putting here in. Because this looks like an instruction.
It's only using three pieces of 5 bits.
Yeah, but the way I'm reading this, I bet you add is this instruction. and having an instruction that starts off with a 0. This is the Little Indian, Big Indian counting that I mentioned, I don't know, day 1 or something like that. You know, the order in which the bits are kind of put into things. But regardless, for the argument of this, when we say computers understand numbers, this is ultimately what we're talking about. These instructions that we're writing that are low-level code, this one-to-one relationship with the CPU, and we've been writing this stuff that looks kind of English-like, kind of human-like. We wouldn't operate very well if you had to write all your code in just these bits, right? So that wouldn't really fly for us. So at the end of the day, that's what this machine code stuff looks like. You know, so we can write an assembly program that looks like this over here in the left, which might not be the friendliest thing in the world, but it's doable. We might not want to write a wall of code with all that 0s and 1s like that. We'd go insane pretty quickly. All right. We've effectively written an assembler, so I think we know what that is. Yeah, I mean, we wrote one, so that chapter we got. Okay. Yeah, and then they give us a simulator, but we wrote our own simulator, so we don't need that. All right, so the next chapter, and then so where we're going to next, so for next week, we're going to look at chapter 4, and then what I'll probably do, I won't give it to you right now, let me think about it for the morning. Well, I'm trying to think what I want to have you do for your homework. Do I want to have you do something related to assembly? I think, yes. No. So you're definitely going to read chapter 4. Definitely read chapter 4 and do all the things. And what we'll do next class.
You just said it.
What?
You said do all the things.
Oh, so that's the example?
No, but you said it.
All right. So for next week, you're going to read all of chapter 4 and do the things. There's always a risk of a quiz, and we'll see. What I'm going to do is I'm going to give you a programming assignment to write something in MIPS assembly. It will be testable on, so you don't have to, I'm asking you to submit MIPS code to me. Make sense?
Mm-hmm.
So you can test it on either the book simulator or you can test it on our scheme thing. I'll give you the updated version of our thing here. But I'm going to ask you to write a program in MIPS that solves some problem. I just have to think about what that's going to be. So it's going to be one of those relatively kind of complexy type things. It's probably going to have you do some subroutines that do some different stuff, do some IO type stuff, and ultimately maybe it's probably going to be maybe a 40 or 50 line program is kind of what I'm imagining, something like that. So I'll come up with some kind of, huh?
So long, but not necessarily.
Yeah, because in 50 lines, we can't necessarily accomplish that much in assembly, but I effectively want you to prove to me that you've kind of picked up on this whole idea of registers and jumps and subroutines and how does IO actually work and that program counter and that kind of stuff. Sound good? All right, so I'll get that to you in the morning. I'll put it in my list, so there will be an official programming assignment that will be to do some MIPS code, and then there will be the reading assignment for chapter 4. Do all of it and do all the things. Do all the things. All right, questions, comments, concerns, bribes?
You deserve an A+.